In this video, I wanted to give a walkthrough of a problem that's been stuck in my head for the last week or so. Some might say I've been nerd sniped about how to solve the flood game. And if you don't know the flood game, it's not hard to pick up on. In this particular version, you control this top left corner by picking other colors. So if you pick red, you'll turn red, and all the red combines. And if you pick orange, you'll turn orange, and that will combine. And the idea is, generally speaking, to keep clicking colors to change your color to flood a color all the way through the map, and after some number of moves, you will have flooded every possible color and turn the entire map one color. So that little blink indicated that I was above the minimum number of moves, and I did not, quote unquote, win. So obviously the solution to this is to write some software. So that's what I've been working on, and that's what I'm going to walk through kind of quickly. I don't want to go through every nitty-gritty detail. But to start, I started off with a screenshot like this, which is this exact same game. And the first thing we want to know is the size of the grid. In this case, it's 16 by 16 cells, and the scale of that, or how many pixels it's actually taking on the screen. And from that scale factor, I'm able to find a pixel coordinate inside every single cell and pull those colors out, automatically make a list of what colors are present in the grid and where they are, and assemble them into a tile object. With all those tiles, I can now loop over every block, which is an individual color, and find which ones are connected and label them a blob. So these 5 orange cells here would be a single blob, and this yellow, red, blue, and the other yellow that's not touching are all blobs of one tile. So I express this as a flood grid object, and the flood grid takes in its constructor an image and information about the size, and then it automatically pulls the colors off of that image. And then it analyzes the blobs, which is very handy for finding out which tiles are together. But to analyze this, I don't really want to look at individual cells. I want to look at the blobs. So the way blobs are connected forms a graph. I divided this into another class to keep the graph functions separate from the tile functions. But the result of that now is, after I've read all the tiles and loaded it into a graph, I can take the image and I can plot a graph indicating how the blobs are connected. So now you might be able to see that when you change your color, you are effectively walking along the graph from blob number 0 in the corner to some other colored blob. And you might get to see that there is something like a direct path. Direct to where? Well, you need to go everywhere. So I thought one thing that might be useful is to figure out which tile or which blob on this graph is the farthest away from the starting point. And I know that the path to that is going to be as short as the game could be. So if I know that let me show this critical path. If I know that blob 175 down here, this orange one, is 23 moves away, I think it's a bit less than that, but if I know that it's so many moves away, I know that the game can't be solved in less moves than that. And the minimum might still be more, but that is one way of looking at this data structure, the graph, and using it to make decisions about the game. But I don't really just want to theoretically do this. I want to actually simulate the behavior and come up with a solution, right? So this is the game tree class. So this graph shows the connection of blobs on a single grid. And we can actually show, in this case, highlight the blobs that are flooded. We're going to start with just blob 0 flooded, but as we select colors, as we perform moves, more cells will be flooded and more of the game map will be filled up. A game tree, in this case, is a theoretical move that we could make and connects a representation of one flood game to another one that has made a certain move. So we are right now in this state. From here, there are two moves. I could pick red or I could pick blue, and both of those would be children of this game tile representation. So what that allows me to do is basically make every possible move from this position and keep hold of those. We're going to score them against each other. The scoring is the way that we determine which one of those moves is the best. And I couldn't tell you off the top of my head which move actually is best just looking at that move. What I would like to do is go more moves from that. And this is the branching factor, or the ply of our search. You could, of course, do what's called a breadth first search, which is where you make every possible move and then you make every possible move that comes after that. But you can kind of tell that if there are two moves here and then there are 2 or 3 moves that can follow that, and the farther you get towards the middle of the board, the more options you actually have because you're touching every single color. Well, the result is that we get many thousands of possible game states just a couple of moves down the row. So I don't have the memory in my computer to check every single possibility all at the same time. So what I'm going to do instead is plot a couple moves in advance, maybe 4, maybe 7, and what I mean by 7 moves ahead is we'll try every possible move and then try every possible move that could come after that until you are 7 moves ahead. And there might be 10,000 possible series of 7 moves that you can make, and we're going to look at all 10,000 or all 15,000 of those possible ones. Then we're going to take the best scoring game out of those 15,000 and actually narrow it down to that one option, and then go 7 more moves in the future. So we might have to do this process of fanning out, trying a lot of different moves, picking the winner, and then fanning out again from that single winner 4 or 5 times, which I'm calling an iteration of the tree exploration. So this is not, it's not coming up with a perfect solution yet. It's not optimal, but I can say that if we just look ahead one move, it might take a fraction of a second. If we look ahead 2 moves, it's going to be a quarter of a second. 3 moves, a half a second. 4 moves, getting close to 2 seconds. 5 moves, getting close to 6 seconds. And 6 moves, 20 seconds to evaluate all the possible games. So after looking ahead 7 moves, we searched 123,000 possible games. It took 80 seconds to compute it all. And the solution it came up with is length 25. But looking ahead 6 nodes got a solution with length 23. So we want the least moves. So this one actually performed better than looking ahead farther. And that's not confusing, but it is disappointing. It means that I can't just throw more computation and always get a better answer. I think I need to experiment more with the heuristics and what makes a game better. Just going by area or the number of tiles covered, you might get some big blobs that are towards the side, but they don't help connect you to the rest of the board, and so all area is not really worth the same, I think. So, but the other thing I wanted to do is actually run this thing robotically. So now that I have all this information about a game, I want to interact with the actual game program, which is what we're going to do right now. In this case, if I give the grid size and help it along by using my mouse cursor to point at the coordinates on screen of the diagonal of all these tile positions. I don't have to be super precise because it's going to average out the mouse coordinates, and it is going to snag this screenshot from my actual screen. Let's not do a bunch of loops, but I do want to make sure we got the scan, come up with a solution, and see what it came up with. It came up with 27 moves from whatever heuristic is set up in there. And if I hit execute, it will take control of my mouse and click away at actually performing the solution it came up with. And you can see it wasn't an optimal solution, but just for fun, let's let this thing go wild a little bit. And for the heuristic, I'm messing with some other ways to evaluate the actual states of the game tree. And what did this do? Let's just do a look ahead of, say, 5. I want it to run a little bit quickly. And now if we press N on the game and hit go again, we can allow this loop to solve the game and immediately execute that solution. So it came up with a solve, and it's able to punch it in. And that one actually was an optimal solution, so not bad. It's solving right now. That one did pretty good too. And this will be the last demo. So that actually is a pretty good performance, I think. 3 out of 3 were optimal. So maybe I just need to mess with the settings. I don't think I'm quite done with this project. I think from here, I want to automate it further and kind of look to bigger and better capabilities with it. For one, I would like it to maybe save the games into a database so I can learn from a huge pile of data. Also, there is a solve feature inside the Flood game. The solver does not purport to be actually optimal, but I think I would like to look for these black dots and have the solver actually save the seed, save the solution that comes out of it, and maybe use that as training data to try to approximate this solver without actually re-implementing it. What else? I have a bunch of other heuristics of different things we can calculate from the game, like the area you are covering with a certain move, the perimeter of your singular blob after you make a move, how centrally you're connected to the graph. It's a measure of how interconnected your blobs are to the other blobs. Uh, Maybe something like a simple rule like chess has, like how much do you control the center, or how many moves along the critical path have you taken. Uh, those sort of things I think can be weighed against each other, and maybe uh, the weights are actually different at the beginning from the end. Like at the beginning, you need to rush for the center or go for centrality, and at the end, you need to stick to the critical path very closely. I'm guessing there, but my thought is that that function of what the heuristic should be can change along with the steps, and maybe that's something I can, instead of trying to figure out myself, I can punch into a neural network to generate its own data and evaluate itself, because really just solving for the shortest path is something it can definitely do automatically. And I think just by clicking along with the game, I've validated that my own code's solutions for the game do actually play out exactly the same. So at this point, I don't even need the flood game. I can just do it all virtually. But I do like the real world, quote unquote, real world application of just slamming the solution into this colorful game at the end and validating that my solution actually works in the game. So that's what I'm up to, and bye.